vector term is itself very new. Earlier it was not in use. Even though mathematicians and physicists were dealing with vector quantities, but the term vector was not there, and this term is very new in mathematical fraternity. So the quantities like related to vectors, people were familiar with these quantities since the period of Aristotle and other Greek philosophers, Aristotle, Herons. So they were familiar with the vector quantities, but they were familiar in different way. So, for example, the parallelogram of rule of parallelogram, which is used to addition and subtraction of vectors. This rule was known since Greek period, Greek antiquity. Aristotle, he studied motion, he studied forces. So all these were vector quantities. So this parallelogram rule was intuitively felt and known to the people of that period, like Aristotle, Plato, and then this parallelogram rule of vector addition is even mentioned in work of Heron's formula, Heron of Alexandria. Heron of Alexandria was a famous mathematician, and we are all aware with the Hero's formula. That is the formula given by Heroes to calculate the area of a triangle. So that formula was proposed by Heron. So even the works of Heron, you can find the rule of parallelogram, which is used to add the vectors. But vectors itself, the field vector, the specialization was itself not so systematic. It was quite vague during the period of Aristotle. Even during the period of Newton, vector term was not in use. Vector was not used to describe the quantities related to like forces and even velocities. Even though we know that Newton had studied all these forces, gravitational forces, he gave the laws of motion. He worked extensively on these vector quantities in terms of gravitational force, laws of motion. But he himself, Newton himself, was not using the term vector. But it's obvious, it's clear that he was quite aware how to add the vectors, how to add these vector quantities like velocity, forces, etc. He was quite aware, but the way he was adding, the way people before 18th and 17th century were adding the vectors were quite different. So even though the triangle law, which we will discuss soon, triangle law for addition of vector was proposed by Newton. He was knowing to add the vectors in his work, in his book Principia. He has mentioned the rule of adding vectors by triangle law, where vectors are added in a sequential manner. He has mentioned in his book that vector can be added in a sequential manner. First you write a vector, then write another vector starting from end of first vector, and then add those vectors by drawing third vector starting from tail and ending at head of remaining vector. So this sequence of adding the vector was known to Newton himself, and he has mentioned in his book this rule of addition of vector. But the term vector came in existence in 17th and 18th century after advent of complex numbers. When complex numbers were represented in a Cartesian coordinate, so the geometric representation of complex number gave birth to modern vector algebra. So vector algebra started And this complex number representation in Cartesian coordinate was widely uh, supported by Frederick Gauss. He was fond of number system, so he supported this complex number representation. And finally, this formal definition, formal representation of vector in Cartesian coordinates was proposed and used by Hamilton. Hamilton extensively worked on vectors, vector quantities. He proposed various notations of vectors which we use today, even though his proposal was quite different, but in slightly modified manner we use vectors presently in our vector algebra and vector notation in physics and other streams. So Hamilton was the last or latest of among all mathematicians who shaped the vectors which we know presently, which we use presently. So this was about little bit about its background, so that you must not feel awkward when talking about vectors, because it has evolved slightly from Greek period to modern mathematics. So it has evolved in a manner because it was known earlier, and in the latest few centuries it was formalized by Hamilton and Caspar. So let us come on vectors. So vectors quantities, these are vector quantities which are defined in such a way that those quantities which are represented by magnitude and direction, such quantities are associated not only with magnitude but with direction also. So these are the vector quantities. Another important thing during defining the vector quantity is not only those quantities which are represented by direction and magnitude. Even though there are few quantities which are represented by direction and magnitude, still they are not vectors. For example, current. You know electric current. Electric current is represented by its direction and magnitude. Still, this is not a vector quantity, because we know that electric current is added or subtracted algebraically. It doesn't obey laws of vector addition. Similarly, speed of light. Speed of light, you might have this phenomena of light, you might have heard in a special theory of relativity, that speed of light is constant for, as per the hypothesis, postulation of Albert Einstein to develop a special theory of relativity. It has been assumed that velocity of light is constant. So velocity of light cannot be added with vectors following the rules of vectors. So these are the quantities like velocity of light, current, which even though they have magnitude and direction, but they don't follow the rules of vectors. So vector is a quantity. We will say vector is a quantity which for representation of vector quantity, first we need magnitude, second we need direction, and third it must obey rules of vector addition. Unlike current and speed of light, velocity of light. So these are the conditions of vector quantities. We will learn about how the vector is represented. Because, for example, if you want to represent mass, this is a mass 5 kg. You can write 5 kilograms of some, let us say this is iron block. So the mass of this iron block is 5 kg. You can represent it like this. This is the representation of a block having mass 5 kilograms. We represent it like this, scalar quantity. This is a scalar quantity. When we use this scalar quantity in formula, suppose for force, mass into acceleration. So we use this directly, 5 into let acceleration is a. So force is 5a. We use this scalar quantity in this formula and put the value of mass 5 in this formula and get the force. But what about vectors? Vectors are slightly different. As we have represented a scalar like this, to represent a vector, we use lines with direction. Suppose this is east, west, north, south. So to represent, suppose let us take an example of displacement. The displacement is given, for example, point A is there, and it is given that another point located at a distance 5 meter from A in east to north direction with 30-degree angle. So this is the point A, another point, so east north 30 degree, east north, this is east, this is north, east to north 30 degree, this is 30 degree, 5 meter away from A. So this is point P and this distance is 5 meter. AP distance is 5 meter and its direction is 30 degree from east to north. So displacement of P from A is represented by vector AP. This is the sign of vector used above points A and P. This means a vector having origin from A and at point P. Origin means tail and it is represented by an arrow. So this vector having AP having magnitude 5 meter and direction 30 degree from east is represented as AP. A is the origin, P is point, head of this vector. This is called head of this vector. Displacement vector having head P and origin A, and this is the sign of vector. Vector AP is represented as 5 meter displacement having direction from east to north 30 degree. 30 degree east to north. So this whole vector is represented symbolically by AP. AP. If I write just AP, that means I am talking about this vector having magnitude 5 meter. This vector is a displacement vector having magnitude 5 meter and direction 30 degree east to north. Symbolically, this vector is represented by this notation. Whenever we write any vector AB, that means A is the origin of that vector, that is called tail of the vector, and P is called the head of the vector, and the direction, that is the directional quantity. Its quantity is associated with direction, so its direction is from A to P. That is the meaning of this symbolic representation. It's a vector having tail A and head. This is also represented as a single letter, let us say A. Sometimes it is represented like this. Symbolically, it can be represented like this. A vector A, when I call a vector A, I am talking about this vector AP having magnitude 5 meter and its tail at A and head at P direction from east north 30 degree. This is also represented as only A, and this A is written in bold letters. It is written in bold letters. To differentiate from normal A, it is written in bold letters. So this arrow sign is also not used many times to represent a vector. With a bold letter, you can represent a vector. So these are all symbolic representations. Symbolic representation of this vector. This vector can be visualized using this arrow AP with the magnitude and direction. So you see a arrow is used to represent a vector. Here we use just 5 kg of iron block. But to represent a displacement of 5 meter from A in east-north direction 30 degree, I will use this arrow to represent it, having direction angle 30 degree with east, magnitude 5 meters. So this arrow is used to represent a vector, and symbolically it is represented by two alphabets. First is the tail of this vector, second is the head of this vector. This is the notation of vector. Sometimes it is also represented by single letter, and many times it is also represented by just by a bold letter. So this is representation of vector. Another important thing you must know at this time, these vectors, when we use vectors, suppose this is a vector A, general vector, which when we just write a vector A and nothing is specified, then it is assumed that it is any vector. It can be any vector quantity. It can be a displacement, it can be a force, it can be a momentum, it can be a velocity, acceleration, any vector quantity. So this is the generalization. We just use a vector A. In vector algebra, when you are dealing with vectors in vector algebra, like you will use cross product, dot product, triple product of vectors, triple cross product, triple dot product. In that time, you will just say use the term vector. It is not defined which vector is this. It is velocity or force or what. Because vector algebra, they just deal with vectors. In vector algebra, we will just deal with vectors. It can be any vector quantity. So when I write a vector A, suppose this vector is represented by this arrow. This vector is represented by this arrow. So this is just a representation of vector. Any vector, it can be represented anywhere. Here also, you can write this vector A. And this is also vector A. Similarly, any vector parallel to these vectors will be vector A. This is also vector A. All vectors having same length and direction will be vector A. So what I want to say, these vectors are not tied at a particular position. As you will see during addition of vectors, you will write vectors, you will place another vector with tail of previous vector or with head of previous vector. So you should not think that these vectors are tied with position. They have direction, they have magnitude, but they don't have position. They can be represented anywhere. It can be written here, same vector, same length and direction. The condition is that only the length and direction of vectors must be same. Then it will be it can be represented anywhere. These all are same vector, representation of vector A. We can write anywhere. All vectors, what these vectors denote, a vector A, which is symbolic representation, having this much length, let us say x meter, and this is the direction, let us say theta from some reference east direction. So all these vectors follow this condition, length and direction. So it can be written anywhere. It cannot be tied at a particular position. Just remember, it is not tied at a position, even though it has a direction. It has a direction, but with same direction and magnitude, you can write anywhere. At any position, you can write the vectors. So this was I wanted to share with you, that never assume a vector with a particular fixed position, because they can be represented anywhere. Yes, their position matters. Sometimes the position of vector matters, but not in representation. Suppose this is a beam. This is a beam, and the force, these are the supports, and the force is acting of 5 Newton at midpoint. So this force has some point of action, midpoint. You cannot assume this force at this point. What is the difference in these two? Because when you will assume a force at this point, the deflection of beam will be different. When you will change the application of point, its deflection will be different. And when you will shift this 5 Newton force just above this support, it will not deflect at all. This beam will not deflect due to this force. This is the deflection during this case. This is the deflection during this case. But in this case, the beam will not deflect at all, because here the reaction force and applied force will neutralize each other. So the point of action of a force matters. But when you will use addition and subtraction of vectors, you will represent this vector. At that time, you need not to specify its position in block in this space. That I want to say. So position of vector matters to study its effect on an object. But when we are representing these all vectors, just these vectors, all these vectors can be represented by 5 Newton. This is the representation for all these 3 vectors. 5 Newton force in vertically downward direction. These force can be represented by this vector. But their point of action matters. To study the deflection and stresses inside this beam, their point of action also matters. So during representation of vector, you can write it anywhere. It has only 2 things, direction and magnitude. Direction vertically downward, magnitude 5 Newton. So you will also doubt that what is the meaning of 5 Newton, how it is related with the length. So that I will also clear. When we are representing a vector, then we assume a scale, an arbitrary scale based on your convenience. You can assume a scale. Let 1 Newton force is represented by 1 centimeter length. You use a scale during representation of vector. So this 5 Newton will be represented by 5 centimeter length. So the length of this vector during representation will be 5 centimeter. This is 5 centimeter length based on this assumed scale, postulated scale. this length is 5 centimeter and its direction is vertically downward. So to represent a vector, we assume a scale. Based on the scale, we draw the line of length corresponding to the magnitude of vector and use arrow to denote its direction. So this is what I wanted to make clear, that a vector during representation can be written anywhere. This is also 5 Newton force with same length and direction. Anywhere you can write it. It is just for representation and operation of vectors like addition. You can add here, you can add here, anywhere you can add. So for that purpose, these vectors are free. They don't tie with a position. But when they are applied on an object like force, in that case, their point of application also matters to study the stresses, reflections and other physical phenomena happening in this beam. In that case, their position cannot be ignored. You have to mention the position. Even the torque about different points will be different based on the position of this point of application. So during representation and operation, their position doesn't matter. A vector of 5 Newton can be represented here, 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 anywhere. But you have to mention its position also. A vector can be described with a magnitude, direction, and for in case of forces and study of its stresses inside a material, you have to describe its point of action, point of application of force also. So it was about representation of vectors. So now we will go through common terminologies used for vectors. Some of these terminologies are zero vector. A zero vector. We know any quantity like mass can be zero. But what does it mean to when we say a zero vector? A zero vector is defined having no magnitude, zero magnitude, and it is associated with direction also. So it must be with undefined direction. A zero vector has magnitude equal to 0 and its direction is undefined. What does it mean undefined? So for example, a particle is moving in a circular path. So we know at any point its velocity is tangential velocity. So it starts from point A and goes through this circular path and again comes to point A. So the displacement of particle is 0 when it completes full revolution, complete revolution. And this displacement can be represented by zero vector. A particle after completing a full revolution, full circular path, completing the circular path comes at its original position. So its displacement at that time after completing one revolution is represented by a zero vector having zero magnitude and direction is undefined, not defined. So these are some ambiguous cases which are not frequently used and you will not encounter such things, but you must have just idea what is zero vector. Similarly, another example, a particle is thrown vertically upward in a gravitational field. It will go up, reach maximum distance and then come down. So it will be projected with vertical velocity v. Its velocity will decrease and at the top point its velocity will be 0. Its velocity will change from upward to downward direction at this top point. So its velocity at this top point is not defined, unambiguous. So in that case you can say the velocity vector at top point is a zero vector. It has zero magnitude at top and its velocity is upward or downward, it is not known. Actually it is exactly zero. So in that case, at top point the velocity vector is a zero vector. So zero vector is defined like this. Another definition of vectors is collinear vectors. Collinear vectors are those vectors which are along the line. As its name suggests, collinear. They are just along the line. It is a line. One vector is this. Say vector can be in this direction or in different direction, opposite direction. Vector A. Another vector. Another vector starts. This vector starts from here and ends at here. Another vector B starts from here, this point. It ends at this point. This is vector B. So A, B, and let third vector which starts from this point and it ends at this point, C. It is in reverse direction. So all these A, B, C vectors are along a line. No matter they have same direction or opposite direction, but they are along a line. So these vectors are called collinear vectors. So these are very simple terminologies which will be used in vector algebra. So I just want to make you aware about these terminologies. Third is coplanar vector. So you know a plane. This is a plane. Coplanar, as its name suggests, these are coplanar. They vector lie in a plane. So let us say this vector A lie in this plane. This vector lie in this plane. A single vector will always lie in a certain plane. Another vector, let us say B. So the condition of a plane, to define a plane, we need at least two vectors. A plane can be defined when at least two vectors are defined, and plane passing through these two vectors will be a fixed plane. So vector A and B, and a plane passes through these two vectors. So I can say two vectors are always coplanar vector. They always exist in a plane. There is always a plane which can be drawn through any given two vectors, no matter what is their direction. Anytime a plane can be drawn which passes through these two given vectors. So two vectors are always coplanar. Let us use third vector. This is the plane where vector A and B lies. A third vector may or may not lie in this plane. It can be vertical like this, or make some angle, any other different angle from this plane. So if a third vector also lies in this plane, let us see. All three vectors are in same plane. So these vectors are called coplanar vector. When vectors more than two lie in a plane, because again I will say two vectors are always coplanar vector. There is always a plane passing through any two given vectors. But for three vectors, they may or may not lie in a plane. If three vectors lie in a plane, then these vectors are called coplanar vector. Another definition is unit vector. So most of the time you will just guess based on the name of the vector. Unit vector means its magnitude is unit. Suppose a vector A. This is a vector A. This vector is representing a 5 Newton force in this direction with a defined scale. So the magnitude of A, I will say 5 Newton force. So a unit vector will be a vector having a direction magnitude unit equal to unit magnitude with unit magnitude, and its direction must be same to vector A. So a vector in the direction of A with magnitude unit is written like this. This means this is a vector, unit vector, by small arrow. This is a unit vector in the same direction, but its magnitude is 1 Newton. Unlike magnitude of A was 5 Newton. So this is represented as vector A by mod A. So if you, this mod A is a particular number, that is the mod A is a magnitude. So a unit vector in direction of vector A is represented like this. Suppose this is a 5 Newton force, so a unit vector A is 1 by 5 A. You will represent a unit vector in the direction of this vector with this expression. This means this is a unit vector, its magnitude is 1. In terms of vector A has magnitude equal to 5 Newton. So 1 by 5, dividing this vector 1 by 5, this will convert this vector in a vector having dimension, unit length or unit force, and dimension along the A. So this is an example when we multiply a scalar with a vector. So there is a vector A. When we multiply a scalar, let K A. This is another vector, let B. Whenever a vector is multiplied with a constant, it converts into another vector having magnitude K times of the original vector. Suppose let A is a vector of 5 Newton in this direction. Let K is equal to -3. This is a number, constant. Then Ka, this is another vector. Let us denote it by vector B. So when we multiply a vector with a constant, it converts into a new vector having magnitude K times of the original vector and direction same. Its direction will be same. If K is positive, this new vector will be in the same direction, and if K is negative, then the new vector will be in magnitude having K times and direction will be 180 degree opposite. So Ka is a new vector where K is equal to -3. So vector B will be represented by this vector. You can write it -3A vector or vector B having magnitude 5 3A, where A's magnitude is 15 Newton, vector A magnitude is 5 Newton. So -3 into A will be 15 Newton in, as minus sign, minus is written here, that means this is a vector in opposite direction of original vector A. So its direction was in this direction, new vector will be in opposite direction. Its magnitude will be Ka, 3 into original magnitude 5, 3 into 5, 15 Newton. A was a vector of 5 Newton force in this direction, hence -3A vector is 15 Newton force in opposite direction of A. So this is how a vector is multiplied with a scalar. Multiplication of scalar, again I will remind you, is a process where a vector is converted into another collinear vector. The new vector will be collinear. It will be in the direction of original vector or it will be in the direction opposite of original vector with magnitude k times of magnitude original vector. K times of original vector magnitude. This new vector will be represented like this, or you can represent like with a new notation, new letter. So this is how we multiply a vector with a scalar. Multiplication of a vector is just process which creates another new vector as a collinear vector of original vector. Third terminology is equal vector. Equal vector, as I have earlier told you, two vectors are equal only when their both parameters, that is magnitude and direction, are same. In that case, two vectors are called equal vector. Let vector A, this is 2 Newton force in each direction. Another vector, it can be written anywhere. I have already told you, B, having 2 Newton force in each direction. So both parameters, magnitude and quantity of these vectors are same. So I will say these are equal vectors. Both these vectors are equal because their dimension, direction and length are same. This is how equal vectors are defined. Another terminology is negative vector. As I have explained you, when a vector is multiplied with a constant, if the constant is negative, then it creates a vector in opposite direction. So negative vectors are defined. Let there is a vector A, magnitude, certain magnitude, this is general vector A, certain magnitude and direction. Another vector with same magnitude and opposite direction, there is a vector B. So we know these both magnitudes are same, their direction are opposite. So we say these are the negative vectors. Minus A vector will be equal to B, or minus B vector will be equal to A. So when we put a negative sign before a original vector, so this whole is a different vector. These both vectors are different. This vector is represented by this arrow, whereas minus A is represented by this arrow in reverse direction. So these are the negative vectors. Or we can say here we are multiplying original vector with minus 1. As I have explained the multiplication of vector with a scalar, here scalar is constant k is minus 1. When we multiply a vector with minus 1, we get a vector in negative direction with same magnitude, and that vector is represented by minus 1. Another important terminology in vector notation is position vector. So position vector you must understand properly because it is widely used in vector algebra in Cartesian coordinate system with right-handed IJK unit vector system. You will use position vectors frequently. So this position vector is, let for position vector. So when we say vector, I have already told you, when we say vector, I mean any vector. It can be, I am just generalizing the term vector. It can be a displacement, it can be any vector. So when in vector algebra, we will just say vectors. We will not say displacement vector, we will not say force, we will not say velocity like this. We are just talking about operation of vectors which are true for all types of vectors, like cross product, dot product, addition, subtraction, multiplication. These are all vector algebraic operations and these are true for all vectors, whether it is velocity, force, momentum, whatever it is. So in vector algebra we will only say vector. Position vector is only defined in terms of a fixed point. Here first of all we have to define a point which is fixed, reference point. You can say reference point. Let there is a reference point O. So this point is fixed. In Cartesian coordinate system you have origin as a fixed point. Similarly for a position vector, let there is a point O. Position, it is, as its name suggests us, position means a vector by virtue of position of a point. There is a point in space, it has certain position. So let there is a point, general point P. You can make a vector OP. O is a fixed reference point. We have assumed a reference point O which is fixed. So this point has certain position. By virtue of its position, we can draw a vector starting from O ending at P, having direction O to P. So vector OP is called position vector of vector point P. Vector OP is a position vector of point P. This is a vector OP. This is position vector of point P. Similarly, another point Q. It has certain different position Q, but this point will be fixed. For OQ vector OQ from tail at O, head at Q is a position vector of point Q. Another point you can take any point P, Q, R. OR is position vector OR. This is OR. O at is tail of this vector, R is head of this vector. So vector OR represented by this vector is position vector of point R, where O is the reference point. This is how position vector is defined. So position vector for a point P is OP. I will again explain you. Where O is the origin, fixed point, reference point, and P is the point, moving point, or it can be any arbitrary point, general point. You can take any point. So this is the point P. Join the point O and P. Join the point O and P. Vector in the direction from O to P, joining, having length equal to OP, will be position vector of point P, represented as OP. O tail of the vector, P head of the vector, and OP, distance between point O and point Q, is magnitude of position vector OP. This OP is a vector having magnitude equal to distance, displacement between point O and P. Distance. This is distance OP, that is magnitude of vector OP, which is position vector of point P. This vector has tail at O, head at P, magnitude equal to length OP. This is how position vector of any point in space are defined. So if it's relative to certain fixed point or reference point. For to define position vector, you must have a reference point. So these were some common terminologies about vectors. So we learned about how vectors are represented. They are represented by a line having an arrow. Arrow denotes the direction. Length of line is proportional to magnitude of vector. Based on the scale, we assume a scale to draw a vector. Based on the scale, the length of vector will be represented, and that representation is such a representation gives us an idea about the direction and magnitude of a vector. And most important thing we have discussed, vectors are not fixed during representation. When we represent them or we add them, we subtract them, we make any operation of vector, cross product, dot product, their position is not fixed. We can draw vector anywhere to carry out any vector algebraic operation like addition, subtraction, cross product, dot product. But in the same time we have also discussed when their point of action, like force, in case of force its point of action also matters. In case of to study stresses, deflection in material, its moment, its angle, its torque about a particular point, they all depend on point of action, point of application of force. So in that case, to study those quantities like torque, stress and deflection, you must also consider their position. But when you are representing a vector, when you are carrying out vector operations, algebraic operations like addition, subtraction, we will discuss quite soon. In that time you need not to bother about their position. They can be represented anywhere. They are free vectors. Vectors are all free for their representation and algebraic operation. So they are not tied at a particular position. When it is multiplied with a constant, it creates a new vector v. So this multiplication of a vector with a constant has certain properties. One is it is commutative. Multiplication is commutative. That means it can be written like this, it can be written like this also. This property of a scalar multiplication with a vector is called commutative property of scalar multiplication. Similarly, there is this scalar multiplication also follow associative law. Law of associative property is that suppose there are two scalars k and l. So you can write like this, or transfer of this bracket doesn't matter. Transfer of this bracket from here to here doesn't matter. This property of scalar multiplication is called associative property. Third is distributive property. Scalar multiplication is distributive also. There are two vectors a plus b. We will discuss what is a plus b. Just we are mentioning that this property, then we can write ka plus kb. So scalar multiplication with a vector also follows distributive property.